students, I welcome you to chemistry lesson. My name is Ndrop Java, and I'll be teaching you today on the energetics. Energetics, this is our topic for today. Energetics, okay? This is the topic which we are going to be looking at. These are our objectives for today. So we should be able to define bond energy, we should be able to describe what an endothermic reaction is, as well as what an exothermic reaction is. Then we should be able to also use the bond energy to calculate the enthalpy change for various reactions. Those are our objectives for today. The three objectives which we are going to be looking at. So we'll start by defining what is bond energy. What is bond energy? Who can define bond energy for us? What is bond energy? How do you describe bond energy? Yes.
This is the amount of energy required to break one mole of gaseous combined substances to form products in gaseous state.
Okay. The amount of energy that is required to break a bond, or the amount of energy that is going to be released when one mole of a bond is formed. That is what is known as the bond energy. Amount of energy. Okay? Bond energy is simply amount of energy. Okay? It's an amount of energy. An amount of energy that is required, okay, to break a bond, or the amount of energy that is released when one mole of a bond is formed. We can refer to the chart which we have here. Okay? Bond energy is simply the amount of energy required either to break a bond or energy released when one mole of a bond is formed. Meaning, bond breaking, you need some energy to break a bond. Then bond formation, for a bond to be formed, energy must be released. Are we clear?
Yes.
Energy must be released. Okay. Now, bond breaking is an endothermic reaction. We come back to our second objective, to describe what is an endothermic reaction. Bond breaking is an endothermic reaction, whereas bond formation is an exothermic reaction. Are you getting the concept?
Yes.
Yes. Bond breaking is endothermic and bond formation is exothermic. The question is now, what is an endothermic reaction? Yes, Ethem?
An endothermic reaction is a reaction that absorbs heat from the surrounding as it happens.
Correct. In an endothermic reaction, heat energy is absorbed from the surrounding to the system. Are you okay? That type of reaction where heat is going to be absorbed from the surrounding to the system is known as an endothermic reaction. It's known as an endothermic reaction. Can we give an example of an endothermic reaction? Example of endothermic reaction. Yes, Doreen?
Photosynthesis.
Photosynthesis. Do you agree?
Yes.
Photosynthesis is an example of endothermic reaction. Let's go to exothermic reaction. What is an exothermic reaction? Exothermic reaction. Yes, Sharon?
This is a reaction where energy is released to the surrounding when it is taking place.
Correct. The reaction where energy is released from the system to the outside environment, it is known as an exothermic reaction. Are we clear? It is known as an exothermic reaction. Example of an exothermic reaction. Example of an exothermic reaction. Yes, Martin?
Combustion of fuel.
Combustion of fuel. Combustion of fuel. It is an exothermic reaction because it releases energy to the surrounding. That is an exothermic reaction. Are we okay? Now, when we are using bond energy, we do calculate what is known as the enthalpy change. The enthalpy change. First of all, we have to understand what is an enthalpy. What is an enthalpy? Yes, Doreen?
This is the total energy of one mole of a substance.
The total energy in one mole of a substance. Or we can simplify it by simply saying the enthalpy is simply the heat content of a substance. Heat content of what? Of a substance. So, to calculate the enthalpy change, delta H, okay? Standard enthalpy change of formation. We use the formula sum of bond energy of reactants minus the sum of bond energy of what? Products. This is the formula that we use to calculate the enthalpy change under bond energy. So, delta H is equal to sum of the bond energy of the reactants minus the sum of the bond energy for the products. That gives us the standard enthalpy change of a substance. Now, if you calculate this and you find that your delta H is positive, if delta H is positive, okay? If delta H is positive, it simply means this is an endothermic, okay? An endothermic reaction. Delta H for an endothermic reaction, it is positive. Then delta H for an exothermic reaction. If you find the delta H to be a negative value, it's a negative value, it simply means that that is an exothermic reaction. Are we getting those two concepts?
Yes, sir.
If delta H is positive, it means it is an endothermic. And if delta H is negative, it means that is an exothermic reaction. Let's look at an example using this formula. Calculate the enthalpy change for the reaction between hydrogen and chlorine gas given the following bond energies. So what are the bond values that we have? We can write this. We have the bond here, and we have got bond energy. Okay, this bond energy is in kilojoules per mole. Okay, kilojoules per mole. This is what we have as it. Okay, so we have this table. We have got the chlorine to chlorine bond. The amount of energy that is required is 242. Then we have hydrogen to hydrogen bond. It is 436. And finally, hydrogen to chlorine bond. It is 431. So we have been given these bond energies. Okay? We have been given these bond energies. So we have to calculate the enthalpy change for the reaction between hydrogen and chlorine gas, given these bond energies, these values for the bond energies. Okay, so we have to calculate. We'll come to this part of the board. The first thing we are supposed to do, we come up with the equation to show us what is happening in the reaction. Okay? We'll come up with the equation. So I'll wrap this. I'll write bond energy there. Okay. Bond energy. There we have. We have to come up with the equation. So we have got hydrogen gas reacting with the gas, reacting with the chlorine gas. This gives us hydrogen chloride gas. Hydrogen chloride gas. We balance it, put a 2 there. So this is the balanced equation for the reaction between chlorine and the hydrogen gas, giving us hydrogen chloride gas. Are we okay?
Yes.
So, what are we supposed to do? We are supposed not to show it in structure form. We have got hydrogen to hydrogen bond reacting with the chlorine to chlorine bond. Then this gives us 2 hydrogen to chloride bond. Gives us 2 hydrogen to chloride bond. Are we okay?
Yes.
So, after we have brought it at this stage, the next thing we have to do is to bring down now the formula. Okay? Our formula is delta H of formation is equal to sum of bond energy of reactants minus sum of bond energy of products. This is our formula. Sum of bond energy of reactants minus sum of bond energy of the products. This is the formula that we are going to use. Now, what are the bonds that we have here? We have hydrogen to hydrogen bond. We have got chlorine to chlorine bond, giving us hydrogen to chlorine bond. These are the 2 bonds that we have. So now, we go back to our bond energy, bond energy, which has been given, which is this one here, showing us the values. Okay? In this equation, we have got 1 bond energy, which is being broken, a bond which is being broken between hydrogen and the hydrogen. Okay. When we have got this, we have expressions like this, using the models of the atoms that we have. We can use these models to show the bonds which are being formed. This is the hydrogen to hydrogen bond that we have. Okay? This is hydrogen to hydrogen bond. Then we have the chlorine to chlorine bond, which we have. Having a single bond between them, a single bond, meaning there are 2 electrons here making a bond. Are we okay?
Yes.
We also have the chlorine to chlorine, which also has got a single bond here. They share electrons so that they become stable. So we have the hydrogen here, and we have the chlorine there. Then when these 2 react, we supply heat energy over the heat energy or heat content. This bond is going to be broken. Okay? This bond is going to be broken, meaning we are now going to have a hydrogen atom which is unstable, it has to become stable. And this other bond is also going to be broken. When these two, which are unstable, they will join and form a bond here. They will form this bond, forming a gas now, which is known as hydrogen chloride, because there is hydrogen and chlorine, giving us this one. Are we okay?
Yes.
So now we have to calculate the bond energy for this. We come back to our formula. This is our formula. We go to the bond values. Hydrogen to hydrogen bond, to break this bond, we need 436 kilojoules per mole. Which other bond are we breaking? We are also breaking the chlorine to chlorine bond. Chlorine to chlorine bond is 242. Are we clear?
Yes.
So we have this, then minus. We have got 2 hydrogen to chlorine bond. We have got 2 hydrogen to chlorine bond. So hydrogen to chlorine bond, this one will be multiplied by 431. 431. So when you add 436 plus 242, what is the answer? Yes, calculate.
678.
678. 678. What this means is that to break these bonds here, these bonds, hydrogen bond and chlorine bond, you need to take in 678 kilojoules per mole. Then, how much energy do you need to take out for the bond to be formed? The hydrogen to chlorine bond. Hydrogen to chlorine bond. So you multiply 2 times 431. What is it giving us? Yes.
862.
862. Okay. Then we subtract 678 minus 862. What is the value we get? What value do we get? Yes, Mwansa?
Negative 184.
Negative 184 kilojoules per mole. Negative 184 kilojoules per mole. Now, what does this mean? The negative value. What does this mean? Okay? What does the negative value mean? Yes, Temweka?
It means that the reaction is exothermic.
It means that the reaction is exothermic. Negative 184 means this reaction is exothermic. It also means that for these 2 moles of hydrogen chloride to be formed, 184 kilojoules of energy must be released. Are you getting the concept?
Yes.
It also means that for the bond of hydrogen chloride to be formed, we need to release heat to the surrounding of how much? 184 kilojoules per mole. This is what it means. You need to release this much for this hydrogen chloride to be formed. Okay, now, this 184, negative 184 kilojoules per mole, it is standing for how many moles? 2 moles of hydrogen chloride. Of hydrogen chloride. It is standing for 2 moles for hydrogen chloride. So, what about for hydrogen, 1 mole of hydrogen chloride gas? How much is it going to take? So, what happens here is this. Therefore, okay, delta H, okay, for hydrogen chloride. 1 mole of hydrogen chloride would be equal to negative 184 divided by 2. Are we getting the concept?
Yes.
Divided by 2, giving us negative 92 kilojoules per mole. Negative 92 kilojoules per mole. This one we have found here. This one we have found here. Okay? This one we have found here is for 2 moles of hydrogen chloride gas. Now, if it's for 1 mole, this is how much energy we need to release to the surrounding so that hydrogen chloride gas can be formed. We can also present these energy changes using what is known as energy level diagram. We can represent this using what is known as the energy level diagram. This energy level diagram we can refer to the chart that we have here. That information that we have calculated there, we have found that energy delta H to be negative 184. We can present it in this form here. Okay? First of all, we have hydrogen to hydrogen bond to be broken. We also have the chlorine to chlorine bond. So this is before the reaction. Okay? Then, when we break these bonds, we are going to have 2 atoms now for hydrogen and 2 atoms for chlorine. Okay? So, how much energy do we take in? The energy we take in to break these 2 bonds, we are found positive 678. This is the total bond energy, amount of energy that we used to break these bonds, these 2 bonds. Okay? Then, from this, we have taken away 862. We have taken away 862. Therefore, the net change, okay, the net change in the energy bar is negative 184. So that when we get rid of 862 from positive 678, we will form a bond which is hydrogen chloride at the end. That one. So this is the representation for the energy level diagram for the reaction between hydrogen and the chlorine molecules to form hydrogen chloride gas. The progression of the reaction is going this way. Then here we have got the heat energy content as it is fluctuating because of the bond being broken as well as the bond being formed. So delta H is negative. The conclusion we make here is it is an exothermic reaction, which simply means because the delta H is negative, it simply means we have to release, okay? We have to release 184 kilojoules of energy to form 2 moles of hydrogen chloride gas. Are we okay?
Yes.
Okay. Example 2. Okay. The question reads, using the bond energy given, using the bond energy given, okay, using the bond energy given, calculate the enthalpy change. Calculate the delta H, the enthalpy change for the reaction. For the reaction below. Okay? For the reaction below. What is the reaction? We have methane, CH4 gas plus oxygen gas, giving us CO2 plus H2O, which is gas, this one is liquid. Okay, this is the reaction that we have. The first thing we are supposed to balance. How do we balance this one? We put a 2 here, and we can also have another 2 there, so that the total number of atoms on each side should be equal. So we have got 1 carbon here. Then we have got 4 hydrogens here, 2 times 2, 4. Oxygen, we have got 2 times 2, 4. Here we have 2 plus 2 times 1, also 4. Okay, now, what are the bond energies given? We have, I'll write the bond energies for this reaction. We have got carbon to hydrogen bond. You need 430. Then we have got the oxygen to oxygen bond. We need 495. Then oxygen to hydrogen bond. We need 467. Then carbon to oxygen bond, we need 745. This is what we are having as the values for the bond energies. Okay. Now, we are supposed to rewrite this one in structure form. We are supposed to rewrite it in structure form so that we are able to identify the bonds which have been broken as well as the bonds which have been what? Formed. So I'll write this equation in structure form now. We have got methane like this with the 4 hydrogen bonds, plus we have got 2 oxygen to oxygen bond, giving us, we have got this carbon to oxygen bond. Then we have plus on the product part. We have got hydrogen to hydrogen bond. How many are there here? 2. So meaning you have to write another one here. Hydrogen to oxygen bond. So this is what we are having. This one we have put here. This reaction here, it is the one we have simplified here in form of the bond energies like this one, which is being formed. The bond energies which is being formed. So we have put carbon to hydrogen bonds, 4 of them. Then we have oxygen to oxygen bond, 2 of them. Then we have carbon to oxygen bonds, there are 2 of them. Then here we have 2 H2O, meaning we have got hydrogen to oxygen bond and hydrogen to oxygen bond here, and even this one the same. So we are now supposed to calculate. Since we have put them in bond form, we have identified that this is how the bonds have been aligned. Okay, so we will now go to our equation. We'll come here. Okay, delta H, okay, enthalpy change of formation is equal to sum of bond energy of reactants minus sum of bond energy of products. This is our formula that we are going to. Now, which bonds are being broken? So we have to identify the bonds which are being broken. So we have got these 4 bonds which are being broken, and these 2 bonds are being broken. So we are going to put an equal sign. Okay. After we have put the equation in structure form, we have written the equation now in structure form, showing the bonds which have been formed. We have got the carbon to hydrogen bonds. 4 of them, they are being broken. Then we have got these 2 oxygen to oxygen bond, they are being broken. So we need energy to break these bonds. When these bonds are being broken, on the other hand, we have carbon to oxygen bond being broken. Here there are how many? 2 of them. Carbon to oxygen, carbon to oxygen. So there are 2 bonds which should be formed. These are not being broken. These are being formed. Then we have 4. In the equation we have written it like this, but when we bring down the picture to structure way, this is what is transpiring on this equation here. It means we have got 4 oxygen to hydrogen bonds which are being formed. These bonds are being formed, these 2 are being formed, and this one and these 4, they are being broken. Are we okay? Yes. We can now go back to our equation, how to calculate the standard enthalpy change of formation. We use this equation which you have already been given. Standard enthalpy change of formation is equal to sum of bond energy of reactants minus sum of bond energy of products. So now, we are going to bring down the values now. Okay? How many bonds of hydrogen to carbon bond are being broken? We have already 4. 4 carbon to hydrogen bond being broken. Then we have got 2 oxygen to oxygen bond are being broken. So this is showing the bond breaking. Okay? Then we take away the bonds which are being formed. We have 2 carbon to oxygen bond which is being formed plus 4 oxygen to hydrogen bond which is being formed as well. Are we okay?
Yes.
After we bring it in this line now, we are going to put the actual values now. Okay? So we have 4 multiply that. Carbon to hydrogen bond. Carbon to hydrogen bond is 413. So we write 413 there plus 2 oxygen to oxygen bond. We have the value there 495. So we put 495. Okay? We close minus. We open 2 carbon to oxygen bond. Carbon to oxygen bond is 745. 745. Okay? Plus 4 oxygen to hydrogen bond. 467. Okay? We close it like that. Are we clear?
Yes.
We bring it down. So now we are going to have 4 times 413. What is the answer? 4 times 413. Yes, Tantola?
1,652.
1,652 plus 2 times 495. 2 times 495. Yes.
990.
We have 990. We close this. We open. Then 2 times 745. 2 times 745. Yes.
1,490.
Come again.
1,490.
1,490. That is Jennifer giving us that answer. Then plus. What is 4 times 467? 4 yes. Talandila?
1,868.
1,868. We close like that. Are we okay? Then we add 1,652 plus 1,000 plus 990, giving us
2,642.
okay. We have 2,642. okay, minus. What is the value when you add 1,490 plus 1,868? Yes, at the back there, maybe? 3,358. Okay. So, this is what it means now. Here's this. It means to break these bonds we have here, these bonds that we have, we need an intake. It has to come in. Okay? We need 2,642. Then, to form these other bonds, we have to release 3,358. Are we okay? So now, when you subtract 2,642 minus 3,358, what value is it giving us? Mwanza?
Negative 716.
Negative 716 kilojoules per mole. This is our final answer. This is how you are supposed to calculate using bond energy. So, since it is negative, again this reaction is what? Exothermic. It is an exothermic reaction. This is how much energy you have to release so that we form carbon dioxide and water when methane reacts with oxygen under combustion. Remember we said one of the reaction, which is an endothermic reaction, is combustion, isn't it? So methane is reacting with oxygen under complete combustion to give us carbon dioxide and the water. To give us carbon dioxide and the water. Any question at this point? Anything? Is it clear?
Yes.
Is it clear?
Yes.
Okay. Okay. We have gotten this concept. How to come up with the bonds, isn't it?
Yes.
Yes. How to come up with the bonds, how to show the bonds being formed. Then again, after the calculation, you can as well present this in a energy level diagram. You can present it in an energy level diagram, just like we did present on this one for hydrogen reacting with the chlorine to give us hydrogen chloride gas. At this point, Learners, we have come to the end of our lesson for today. We have gone through all the three objectives that I gave you at the beginning. We defined bond energy. We have described endothermic and the exothermic reactions. We have also been able to calculate the standard enthalpy of formation for various substances as indicated in our objectives. My name is Ndlovu Java, and on behalf of the production crew, it's bye from now until next time.